Hey, welcome back to our discussion on thermochemistry and specific heat. So remember in the last video we learned that when we solve for Q using these three variables, we are solving for the amount of energy in molar heat. But since there is an equal sign in this equation, that means that we could technically solve for any one of these variables if they're missing. So if we're given 3 of the 4 variables, we can use algebra and solve for the missing variable. So that's because there's an equal sign. So if we were going to look at this algebraically, here's what that would look like. If we wanted to solve for M, we're putting Q over the specific heat and the change in temperature. So if we have our original equation, this is how we get that. Q equals M times Cp times delta T. If we are asked to solve for the mass of a substance, we're just going to divide by Cp times delta T so that we can cancel those. And what you do to one side, you have to do to the other side. So that's where we got this. M equals Q over Cp times delta T. We're doing the same thing for all of the variables to solve for specific heat. We're going to divide by mass times delta T. Mass times delta T. And to solve for delta T itself, we're dividing by mass and specific heat. So you notice on all of these variables, Q ends up being on top. And that's because it's the only thing on that side of the equal sign. So if you're not solving for Q, just put Q on top. It's pretty simple. So what I'm going to do is I'm going to go through a couple of problems that are on assignment number 3. On my website, this is assignment number 3. And it's going to have you solve for each one of these variables in different questions. So I'm going to pick one of each type and solve that for you, and then you guys will be responsible for doing the rest as assignment number 3. Okay, so we're going to start with the first one here. So we're talking about a piece of copper alloy. So an alloy is a mixture of metals. So copper alloy means that it's mostly copper, but there's other metals in there like zinc and maybe some nickel or something in there that's making it harder. So it's a mixture. And so we've got 85 grams of that, and it's heated. So the temperature is increasing by 15 degrees Celsius, and it's absorbing 523 joules of heat. So that could be from a stove or from the sun or whatever. So we're going to approach this kind of like we did with gas law questions. We'll make a list of all the variables. So I've got a Q, an M, a Cp, and a delta T. So in this case, my Q is 523 joules. 523 joules. Whoops. My mass is 85 grams. My specific heat, that's what I'm solving for, specific heat. So that's my question mark. And my change in temperature is 15 degrees. So remember, I can say 15 degrees Celsius or 15 degrees Kelvin because the change in temperature is the same for both. So now all I'm going to do is solve for this. So if I want to solve for Cp, I'm going to use this equation, Q over M times delta T. Q over M times delta T. And I'm just going to plug in those values. So my Q is 523 joules. My mass is 85 grams. And my change in temperature is 15K, 15.0K. Okay, so we'll solve for that. So we're going to do 523 divided by, remember we're going to use parentheses on the bottom because there's 2 values. So 85 times 15, 85 times 15. so there's our answer, 0.410. So you're rounding to 3 digits, so 0.410 joules per gram Kelvin. None of these units cancel out, joules, grams, and Kelvin, so we're keeping all of those. So when we have specific heat, we'll always have 3 units like this. It might be degrees Celsius or Kelvin, but it's always going to be joules, grams, Kelvin. So 0.410 joules to make 1 gram go up 1 degree. That's pretty low. Remember, water was 4.18. Okay, so this one, part B, is asking for energy. What variable are we solving for there? That's Q. Okay, so we have the same list of variables. We've found Cp is 0.410 joules, gram, Kelvin. So now we're going to solve for a different Q. So instead of 523, it's asking how much energy will the same sample lose if we cool it. So what's our delta T this time? 45, sorry you couldn't see that, 45 down to 25. Our delta T is a 20-degree difference. So we're solving for Q. We're going to use the original equation. Just multiply all 3 of those variables together. Okay, so M, our mass, same sample they said, so it's 85 grams. Our Cp, we just figured that out, is 0.410 joules, gram, Kelvin. Our delta T, it's a 20-degree change. So it's 20 Kelvin, degrees Celsius or Kelvin. Remember, the temperature change is the same in Kelvin or degrees Celsius. So let's multiply all those and see what we get. So 85 times 0.410 times 20. 697 what? 697. So look at all these units that can cancel. We can cancel grams, Kelvin, and we're left with joules. So this is joules. So that's how much energy that copper alloy lost as it was cooled off. Almost a kilojoule. Okay, so I'm going to come down to the bottom. You guys can handle number 2 and 3. So 4 and 5, we're going to look at those. Because 4 is asking for a final temperature, so we're looking for a delta T. Okay, so we've got a Q, we've got an M, and we have a temperature in here. So let's make our list. So we've got a Q, M, Cp, and delta T. Okay, Q is 420 joules, M is 35 grams, that's only 2 digits. Specific heat, so it does say water. So this is from the last video. We know the specific heat is 4.18 joules per gram Kelvin. And that's from this chart right here, 4.18 joules gram Kelvin. So we're looking for a delta T. So how do we solve for delta T? Okay, so remember we put Q on top over mass and specific heat. Q over mass times Cp. Okay, so our Q is 420 joules. Our mass is 35 grams. And our Cp is 4.18 joules, grams, Kelvin. So let's cancel units. We can cancel joules and grams, and we'll be left with Kelvin. So 420 divided by 35 times 4.18. We get we have to round this to 2 digits because of that value right there. So that would be 2.9. 2.9 Kelvin. Now remember, this is a difference. This is how much the temperature changed. This wants the final temperature. So if we started at 10 and the water is having energy added to it, that means that the temperature must be going up. So since this is in Kelvin, I decided to do this in Kelvin. Let's take our 10 degrees and add 273. So it's a 283 Kelvin is where the water temperature started. So 283 Kelvin, we're just gonna add that change in temperature to our original temperature. So 283 plus 2.9. We have to round this, right? 200, and we need 0 digits after the decimal. So this will round to 286. 286K. So that's our new temperature after energy was added. So it didn't go up very much because water has a very high specific heat, which means that it can absorb heat and not change temperature very much. If we added that much energy to our copper up here, we would have seen that temperature go up a lot more. Okay, last one. So number 5 down here where it says mass, we're solving for mass, M equals. So we have water. Let's make our list. We have Q, M, Cp, and delta T. Let's see. We have a Q, 24,000 joules or 24 kJ. Lots of energy. Mass we're solving for. Cp, we know it's water, so it's 4.18 joules per gram Kelvin. And our change in temperature, okay, so it says it starts at 25 at room temperature and it's raised to boiling. That's at 100 degrees Celsius. So what's our difference in temperature? It goes from 25 to 100. That's a difference of 75 degrees. So that's my delta T, 75 degrees Celsius. Okay, so we're solving for M using this equation, Q over the other two. So Q over Cp times delta T. So our Q is 24 kilojoules over Cp. Now look at how this is different. Q is in kilojoules, but Cp has joules. Those units don't match, so we do have to change these units to joules. So how many joules would that be? Kilo is 1,000, so that'd be 24,000 joules over our specific heat, 4.18 joules per gram Kelvin, times our change in temperature, 75 degrees. Okay, let's calculate. 24,000 divided by 4.18 times 75. Okay, 76.6, or to 2 digits we have 77. 77. Okay, what do we have 77 of? So joules cancel, degrees cancel, so we're left with grams. So that was 77 grams of water. We added 24,000 joules of energy to 77 grams of water, and it only went up 75 degrees Celsius. That's, again, because water has a very high specific heat. Okay, so that's how you do it. That's how you solve for any of the 4 variables. So here is the answer key. These are the number answers for all of the questions that are on that worksheet, which is assignment number 3. So you can pause the video and look at those answers.